Okay, let's begin. So for the project, I've already got a couple of questions on how to do certain things related to demand estimation. You've got until Thursday of next week to prepare your draft summary and calculations. And sometimes draft is an uncertain word. Sometimes draft means crappy job, and sometimes draft means you're going to have another opportunity to make revisions. And in this case, it's the latter of the two. I still want it to be clear. I don't want to be confused when I'm trying to go through how you made certain assumptions and how you did your calculations. It should be very easily communicated and easy to understand, but I'm going to give you the chance to make changes, and so your grade will reflect effort. You know, I'm not going to have the same standard of quality as far as the actual answers you get here as I will in the final version after I've given you feedback. So that's due Thursday the 6th. If you've got questions along the way, feel free and let me know. So part of the reason why this homework 7 is due on Tuesday is so that then you don't have another homework assignment on the plate at the same time as you're working on those demand estimations. And the other thing is that really, homework 7, all of those problems, with the exception of the handout, all of these problems from the book hinge on Q equals VA. Just different ways to solve the continuity equation. So they look complicated, but they're really not that bad. They're ultimately just implementations of the continuity equation, with the twist that I'm going to tell you about today. So any announcements, questions?
Is that draft something that should be tied?
No. Remember, I mentioned that I'd be delighted to see your handwritten calculations as long as they're neat and easy to understand. If you'd like to use a spreadsheet or a word processor for the demand summary, then you can, but your calculations need to be provided, and so is that the sheet that I gave you. There's a table at the end of the packet that has like the summary of all the different components and then the peaking factors and the totals and so on. All right? Okay, today we're going to be talking about some information from Chapter 10. We're changing gears in the course. The first 2/5 of the course is closed conduit flow. And now for the remainder of the semester, we're going to be talking about open channel flow. You've had closed conduit flow before. Back in fluid mechanics, Chapter 7 dealt with flow through pipes. And so the first part of the course was probably more familiar to you than the next part of the course is going to be. But so many of the same laws apply, it's just we're applying them in a new set of circumstances. So let's review what's familiar and what still applies. Okay? In open channel flow, there's still uniform flow. Uniform being that the velocity is constant in the direction of flow. That means that the streamlines are parallel. And in non-uniform flow, for example, if the banks are getting closer together in a river, that would be an example of non-uniform flow. The velocity would be changing in the direction of flow if the banks were getting closer together or further apart, or if the depth was changing. You know, there's a variety of things that can cause non-uniform flow. Uniform flow is usually only seen in a man-made channel. Out in nature, where the channel is irregular, continually changing its direction and slope and materials, more commonly flow will be non-uniform. Okay? Some of the lessons we learned about steady versus unsteady flow still apply here in open channel circumstances, where steady flow is the constant flow with respect to time, meaning that the velocity is the same, the depth is the same now as it will be at some point in the future. It means the flow rate is steady. Things aren't changing over time versus unsteady flow. So here's an image that depicts, for open channel, the difference between the flow condition at the beginning of some interval where a culvert's starting to be washed out and the road that is above the culvert is starting to collapse into it. And then sometime after that event, after the water is completely damaged the bridge and there's no more pavement going over there. So unsteady flow means that the flow conditions changed over time. Now channel types, there's a couple of different channel types, and the first of these is prismatic. In a prismatic channel, that means that the cross-section is regular. It's easy to characterize because usually in a prismatic channel it has some sort of a shape that we're already familiar with. A rectangular channel is prismatic. Here is a trapezoidal channel being depicted. A triangular channel. All of those have shapes that are regular, and beyond the cross-section being regular, so is the profile. If you look at the side view of an open channel that's prismatic, this solid line represents the bottom of the channel. The dashed line would represent the water surface. You can see that the slope from one point to the other isn't changing. It's just a regular cross-section that wouldn't be that way in nature, but if we have lined a channel with concrete or asphalt or clay and been very careful about it, we can maintain a prismatic channel. And in top view, you can see that it's not meandering. It's just a straight line, essentially. Now compare that to a non-prismatic channel where you do have variations in any one of these or in all of them. So variations in the shape. Think about the Ohio River and how there are little islands at certain spots and the depth is changing. At one section it may be deeper than the other. So that the way they find out what the depth of a river is they'll go along the surface of the river and they'll push poles down, or they'll put leads on lines, and they'll find out what the cross-section looks like. And defining the underwater environment is called bathymetry. Underwater geography is bathymetry when you're trying to find out what the shape of the cross-section looks like. So instead of a prismatic channel, which is a very easy to characterize geometric shape, a non-prismatic channel is irregular. And if you look at it in side view or in profile, you can notice that although the water surface is relatively constant, that the channel bottom is irregular. And actually, this is a simplification because the water surface would also be a little bit irregular. In the second part of the open channel segment of the course, we're going to be talking about gradually varying flow and how does the water surface respond to changes like this. You know, when does it get deeper and shallower, and how can we predict what the depth is going to be upstream when there's some kind of an obstruction. Finally, if you look in top view to a non-prismatic channel, it might be that it's a meandering stream. And a channel is often going to meander in order to achieve some slope that's consistent with the resistance of the soil. You know, a stream won't go straight down from point A to point B if it's going to scour the soil too much, if the velocities would be too high. And so sometimes it meanders back and forth like you might, if you're skiing a slope of a mountain, going back and forth allows you to achieve a different channel bottom slope. So prismatic versus non-prismatic. Now, you've got this table in your text. This is table 10.1. We're in chapter 10 now. Chapter 10 is all about channel geometry. Really useful table for all these different shapes and the formulas for the area of the flow. So for a rectangle, obviously, it's going to be the width times the depth. We've worked with trapezoidal geometry before, and we've talked about how the side slope of a trapezoidal channel has this parameter t, where t is the horizontal component of the side slope, where 1 is assigned to the vertical component. So if t equals 1, that means the side slope is at a 45-degree angle. Some of the more challenging geometries to work with would be a circular conduit that's only partially full. And we will get to the geometry of a circular, partially full conduit when we're doing sewer design. Because if you think about a sewer pipe that's circular, it's not always full. In fact, it's very rarely full. It's extremely bad news if the pipe's all the way full in a sewer, because it means that the pipe is pressurized, and a pressurized sewer pipe is going to leak backwards into people's basements and yards. And so the geometry of a circular, partially full channel is it's hard to deal with, but we'll get there. One last thing I wanted to point out is here's a parabolic section, the formulas for a parabolic section, and one of your homework problems has a parabolic section, and so I wanted to emphasize that the formulas are provided in table 10.1 for that assignment problem where they're saying the channel is approximated by a parabola.
What's a B star? Oh, okay, yeah.
Yeah, what they're saying is that this formula for the wetted perimeter is only valid for a certain range of depth to width. So if you have a parabola where the depth is very small relative to the width, then this approximation wouldn't apply.
The T of the one,
Mm-hmm.
in some of the earlier homework problems, it was given as like,
V to H ratio.
yeah,
Yeah, so here 1 is the V and T is the H. So if you said that there is a trapezoidal channel, and usually what it would say is a trapezoidal channel has a 1 to 2 side slope, and they may not even say which is the 1 and which is the 2. It would just almost go without saying that 1 is the vertical and 2 is the horizontal, because you wouldn't have a trapezoidal channel that's really steep where it would have 1 to 2. That, especially for a soil line channel, that would just be simply too steep. Yeah, so vertical, horizontal, where T is what we are calling the horizontal component of that side slope. Okay, so what did we talk about? Ways to classify flow. Classify flow as uniform, non-uniform. We classify flow as steady, unsteady. We can classify the flow going through a channel that is prismatic or non-prismatic. Previously, we've already learned about laminar flow versus turbulent flow. And you can do the same thing in open channel. You can classify flow as laminar and turbulent. So consider a stream where, I'm very proud of the sequence of animations here. It took me hours a couple of years ago, but still, it took me hours, the sequence of animations. So tell me that it was worth it. So we've got a stream bottom. This black line's a stream bottom, obviously. And we've got a water surface, and the water is going along. Now, already we've got a problem, because what we know from fluid mechanics is that the velocity at the bottom of the channel is lower than the velocity at the top. So I guess I should alter my diagram to make it so that those little velocity vectors are shorter at the bottom. But you'll forgive me temporarily. This is more about the, oh, there it is. Okay. So there's the velocity profile. And the Reynolds number below 2,000 means that we've got a laminar zone. So why is it that we have a laminar zone close to the stream bottom?
Where it held back.
Okay, that's the key, is that the velocity is low at the bottom of the channel because that's where the resistance is. So the further away you get from the resistance, as you go up through the channel, you're getting further away from that surface that's applying the resistance to flow, and so the Reynolds number is increasing the higher you get. At the bottom of the channel, the Reynolds number is 0, because right at the very, very bottom, the velocity is 0. But you can go up some distance and still have laminar flow. So there are these roughness elements that project into the flow, and it's smooth turbulent flow when the Reynolds number in bulk, overall, the average Reynolds number is going to be turbulent, but smooth turbulent flow is when overall is turbulent for the average velocity, but then whatever projections we have are fully cushioned and encompassed by the laminar zone. Transition is when these roughness elements are at the same height as the transition between the laminar and the turbulent zone, and then rough turbulent flow is when the roughness elements project into the turbulent zone. Later on, whether it's smooth turbulent flow or rough turbulent flow, those classifications will help us to understand how the water behaves as it flows from point to point, how the depths may change. So this is just an introduction to different types of flow, and so I've thrown that slide in there just to remind you of the effect that if you have the roughness elements fully cushioned by the laminar layer, then the flow above it is going to be affected differently than if those roughness elements project outside of the laminar layer. Okay, so we're talking today about similarities and differences. And so similarities is that we still have many of the same tools that we've used till now. We still have the continuity equation. I already mentioned that the bulk of your homework problems are somehow applying the continuity equation. So in an open channel environment, if you've got a rectangular channel, let's say, and they say that the velocity of flow is 1 meter per second, that's into the page. The water's moving along at an average velocity of 1 meter per second. And if you knew that the channel of the bottom channel width is 2 meters, and the depth of the water was 1 meter, so then area is 2 meters squared. So the flow rate is VA. In this case, it would be 1 meter per second times 2 square meters. So Q is 2 cubic meters per second. Continuity still applies in an open channel. Area is just the cross-sectional flow area where water is present. Sometimes the tricky thing is when they would, let's say, give you the flow rate and give you the channel width, but they wouldn't tell you the depth. And so sometimes you'll be solving for some component of the area. If they said flow rate is 2 cubic meters per second, and they said B equals 2, but what if they said the depth is unknown? So from that, what you'd say is, well, we know, and I guess we already specified the velocity is 1 meter per second. So if you know the width, you could say that the area is 2y, and you know that Q is 2 cubic meters per second, and you can find out what the depth is by Q equals V, which is 1 meter per second, times A, which is 2y. So sometimes the tricky part of continuity equation is when they're asking for one of the geometric attributes, whether it's the channel width or the flow depth, something along those lines. You'll get some good practice on that. Momentum equation is that idea that there's a force required to hold the system steady. Remember that in words, when we were interpreting this equation, we said the force required to hold the system steady. So what we would do is we'd have some box that a jet of water came into and a jet of water came out of, and then we would do a force balance, and we'd say the force required to hold the system steady in the x direction. We'd look at the flow in minus the flow, it's actually the flow out minus the flow in. So V2 would be the velocity out, velocity in, and we kept track of positive x was in this direction, positive y was in this direction, and then it was from that we were able to find out how hard we'd have to push this way or that way in order to hold the system steady. So the way that we apply the momentum equation in open channels is by, first of all, thinking about the shear stress. There's an equation that says the shear stress is a function of the unit weight of the water, the hydraulic radius. So R here is talking about the area divided by the wetted perimeter, and then the slope of the energy grade lines, S sub F. The slope of the energy grade line, which is talking about the head loss relationship. So if we take what we know about head loss from the Darcy-Weisbach equation and substitute that in here, then ultimately we can derive the velocity as a function of the friction of the surface and the slope of the energy grade line. So think about a force balance for some element of water. You can see here's a channel bottom, and it looks like the water surface, the depth is decreasing in the direction of flow. And that could be for a couple of different reasons. It may be that in this case the flow rate is increasing, like I'm saying that it's unsteady flow, and so that's why there's this big wave of water coming. Or it could be that water is about to flow off the side of a cliff. You know, if you had a river going downhill like this, but then there's a cliff, what happens is the water's going to have some depth, and it's going to get more shallow before it flows over the side. So in a case like this, we could do a force balance in the direction of flow. We've got the hydrostatic forces, just the function of the increasing pressure at a certain depth. So there's an equivalent force acting in the direction of flow because of the hydrostatic forces that are a function of the depth. The same thing at 2. There's a force acting this way on the element of water that is our control volume because of hydrostatic forces. Here are the forces that are due to the shear stress. Shear stress acting over some surface area. The width of the channel, the delta x is the length of it, so there's a shear stress component resisting it. Some component of the weight of the water is going to be in the direction of flow. And through doing that force balance, we can, through doing that force balance, we can find out why the water surface is changing. That's implementing the momentum equation is how we're going to do the water surface profiles and the gradually varying flow depth calculations. There's 3 methods that we'll learn later in the semester that are sort of spreadsheet intensive methods. The numerical integration method, the direct step method, and the step-by-step method. In open channel flow, the HGL, meaning hydraulic grade line, is the water surface itself. In closed conduit flow, the HGL was some imaginary line that was above the water surface. Inside of, in a pressurized pipe, the HGL was above the pipe because the water was under pressure. If the water's not under pressure, then the HGL is the water surface. And the EGL is above the water surface, the distance of the velocity head. So the EGL is this dashed imaginary line, and it's above the water surface a distance of, here's the HGL, here's the EGL, and the distance between the two is V squared divided by 2G. The way that you find the EGL is you take the water depth and add the velocity head. The energy equation is the third and final primary fundamental equation that we apply in open channel flow. And there's some differences from the way that it's applied in the pipe to the way that it's applied for an open channel. In a pipe where water's flowed confined in a conduit, remember I just mentioned that the water is pressurized. In a channel that's open to the air, the water isn't pressurized any longer. And so we're not going to have pressure head when we transform the energy equation for use in an open channel environment. We also don't have pumps in the same way that we do for a closed conduit flow when we're working in terms of open channel. And so if we translate the energy equation for use in open channels, what we were calling the pressure head, instead we're just going to have the flow depth. Velocity head is still there. And Z, which is the elevation above some datum, is still a part of our thinking. You'll notice there's no pump head term. And also, here I'm saying H sub F instead of H sub L. H sub L included 2 components. It included local losses and friction losses. But there aren't local losses in the same way for an open channel that there are for a pipe. Like a valve that would close off or a pipe bend. You don't really have those same sorts of things in an open channel. There are transitions in width and there are steps that can take a little bit of energy out, but we usually handle them separately, and so they're not included in the energy equation in the same way that we throw local losses into the energy equation for pipes.
So if you were going from an open channel into a pump, you just calculate to that point, and then where it goes into the pipe?
Well, so you're saying if you threw the suction side of a hose down in here?
Well, no, like if your channel was running into like a culvert kind of pipe.
So it's going to become pressurized? That's a pretty specialized application. You'd say So you're asking, what would be the energy loss at the transition?
Well, yeah, I mean, yeah, I just mentioned.
Yeah. That would be similar to when we will talk about what happens when a channel width changes. It's a term that you'll just sort of manually insert to the equation. You'll put it on the right-hand side of the equation as though it was a local loss. But those are the exception rather than the rule.
Are we still going to leave alpha out? Or
Yeah. We usually won't bother calculating the kinetic energy correction factor alpha. So alpha equals 1 for our purposes. And it's only when we have truly laminar flow and a parabolic velocity distribution that alpha is 2 in case of the closed conduit pipe. But in the case of open channel, alpha really never would be 2, regardless of what the flow rate is, because it's open to the air at the top, and so it won't have a parabolic velocity distribution. So alpha will be 1. So in summary, continuity, momentum, and energy. Momentum gets changed around. Remember, we did a force balance, and I said that factors into how we find out the energy loss. How much energy is lost as the water moves from point to point. That's a momentum type equation, and we can think about it in terms of Darcy-Weisbach, where F is referring to a friction factor. But more commonly, we'll use what's called the Manning or the Strickler equation. I'll call it Manning for the rest of the semester. This is the only time I identify it as the Strickler equation. But the Manning's equation has, remember, a simpler n value that doesn't vary with flow velocity. And somehow that's less of a problem in open channel flow. If we wanted precision in pipe flow, it's really important for us to have an F value that changes with flow conditions. We didn't get as good results when we used the Manning's equation or even the Hazen-Williams equation in closed conduit flow. But Manning's equation is okay for open channel. It's not as precise. Open channel calculations are inherently less accurate than closed conduit calculations, and maybe that's why we don't worry so much about the fact that the n value is constant, is because everything we're doing is less accurate to begin with. If you want to find the flow rate, Q, using the Manning's equation, then you just have Q equals A divided by N, R to the 2/3, slope to the 1/2. So, Q equals VA. The equation here is expressed in terms of V. So if you want to use the Manning's equation to find the flow rate Q, then you would just multiply this whole expression by A, as I've done on the board there. S, that it's talking about, Manning's equation only works for uniform steady flow. If you don't have uniform flow, Manning's equation isn't going to tell you how deep the water is. Non-uniform flow or gradually varying flow is something we won't tackle till a few weeks in the future. So the Manning's equation, maybe off in the margins, put a little star and say only use Manning's equation for uniform flow. During the exam, I was walking back and forth and I was amazed at the equation sheets that you put together. They were very exhaustive. I saw so many equations there. And I remember doing similar stuff like that when I was a student. And sometimes I'd put the equation, but I wouldn't remind myself when to use it. And so I'd see an equation, oh, Q, I'm trying to solve for Q. I'll use this equation. But it only applies under the right circumstances, and only use this if the flow is steady and uniform. Otherwise, you get a false result. So S, uniform flow, all the slopes are parallel. In uniform flow, the channel slope is parallel to the water surface, and the EGL is parallel to both of them. So we've got S naught is the slope of the channel. S sub F is the slope of the energy grade line. And just S, what we're talking about, the slope of the water surface is parallel to the both of them. All right? Now, one last thing I wanted to say about the energy equation is H means head, and remember, head is the sum of the three terms of the energy equation. So the sum of the depth, the sum of the velocity head, the sum of the elevation above the datum, z, those three terms together, we'd add all that energy together and call it head at 1. So the head at 1 is equal to the head at 2 plus the local losses. So what this means is that there used to be more energy at 1 than there is at 2, and H sub f is how much was lost between the two. You had a lot of energy at 1, you've got less at 2, and here's the difference. This is what was lost as you went from point 1 to point 2. So here is 1, here is 2. How much energy is lost from 1 to 2? Here was the energy at 1. If we draw a straight line, this is the head loss between 1 and 2. It was how much the energy grade line went down. Or you could look at it the other way. You could say, you know, we lost all this. If this is our z datum, we used to have this extra elevation at 1. So this amount right here is the same as the H sub f. Since all those are parallel, those three lines being parallel means that the delta z between 1 and 2 is equal to the H sub f between 1 and 2. So uniform flow, delta z is equal to H sub f between the 2 points. I had the hardest time understanding when I could use the Manning's equation when I was an undergraduate student. I guess I didn't pay attention enough when we were talking about steady, uniform. The flow classification and the flow visualization, I was tuned out during that lecture, and then I didn't know when I could and couldn't use the Manning's equation. So you can use Manning's equation when all three of those slopes are equal. And I would see S in here, and I'd say, well, which S is it? It's any of the three because they've got to be parallel to use it. Okay, here's a little example that we're going to take a look at. And I phrased this problem very similar to how one of the problems from your homework is phrased. All right. Okay, we've got water flows from 1 towards 2. 1 is always upstream, upstream, downstream. Sometimes we talk in terms of headwater and tailwater. Usually we use those phrases of headwater and tailwater when there's some sort of an obstacle or an obstruction in the water that's causing non-uniform flow. But still, even here, when we do have uniform flow, sometimes people will say headwater and tailwater. Headwater means upstream, tailwater means downstream. Okay, so at 1, the riverbed is 0.78 meters above, 782 meters above the datum. So here's our horizontal datum, and the elevation of the riverbed above that datum is given, 0.782 meters. And the bed width is 0.5 meters. So that is talking about the width of the channel, lowercase b. Some formula books for channels will say like lowercase b and then uppercase B for the top width, or sometimes they'll call it T for the top width, capital T. And in fact, I don't remember what the FE equation packet says. Anybody got it there? Let's take a look and see what variables the FE equation manual is saying you should use for the top width. I'll have a look at that one. Thank you. They're saying T for the width of the water surface. It's on page 163. So they use the term T for the top width. Okay, so Here in this case, our channel width is 0.5 meters, and we know the average flow velocity is 0.55 meters per second. And the total energy at 1 is 1.451 meters. So let's try and make sense of all of this, first of all, so that we can find out what the water depth is at 1 and what is the flow rate. Okay. Z1, 0.782 meters. B, the bottom width of the channel, and since it's rectangular, also the top width is 0.500 meters. And the velocity is 0.55 meters per second. And the total energy at 1 is 1.451 meters. Total energy at 1 is also talking about the head at 1. It's the sum of all three terms, the elevation head, the velocity head, and the depth. Okay, so total energy is those three terms. Y1 for the depth, Z1 for the elevation above the horizontal datum, and then V1 in the velocity head term. Okay, we're going to try and find out what's the depth of water at 1. So let's rearrange that equation to be in terms of the depth of the water at 1. So Y1 is going to be E1 minus Z1 minus the velocity head. So that if we know that the total energy at 1 is 1.451 meters, and that location 1, the channel bottom, is 0.782 meters above the horizontal datum, and then we subtract the velocity head. So the velocity head is going to be 0.550 meters per second squared divided by 2 times 9.81 meters per second squared. This velocity head term is 0.015 meters. Pretty small relative to the total energies that are involved. Y1 is 0.654 meters. So we know the depth of flow at 1 because by definition the total energy is 1.451 meters. So the only thing missing from that was the depth. So when water flows downhill, it's losing energy because its elevation is decreasing. And where is the energy going? It's being lost to the resistance put up by the channel. The channel is resisting its motion, and so the energy that's being exerted is an energy that's essentially scouring the soil. As water moves over the channel, it scours sediment, and that's why there's so much in the way of sediment deposits in New Orleans and where the Mississippi River stops. Is it starts fanning out into the ocean and dropping the sediment, and the Mississippi River Delta is because all that energy of scouring the banks of the Mississippi River, eventually those sediments are deposited. So here we can find the depth of flow, and we want to know the flow rate. It's just going to be Q equals VA. Excuse me. 0.55 meters per second. And the cross-sectional area is 0.654 meters times the channel width of 0.500 meters. and that means our flow rate is 0.180 cubic meters per second. Pretty simple stuff once we get familiar with the terminology for open channels. Any questions about that? We're making better time than I was expecting. We might be able to go over the solution at the end of class for the exam. Okay, this is a question that came up as you were preparing for the exam. Remember, we talked about that the horizontal length of the pipe and the inclined length of the pipe aren't the same, but they are so close that it really doesn't make any sense for us to keep track of the cosine of the angle. And the same thing is going to be true in open channels. So if you consider that a certain length of the channel, L, is an inclined length where delta Z is the elevation difference of the upstream end is that much higher than the downstream end, then the angle is usually so small in open channels. A steep slope in a channel would be a 2% slope, or a 3% slope would be quite steep. And more commonly, the type of slopes for a river would maybe be 0.5%. And so those slopes are so small that L and the cosine of L, the cosine of the angle is going to be 0.999, very, very close to 1, so that the length and the inclined length are essentially the same. So we won't bother to differentiate when I say that location 1 is a kilometer upstream of location 2. You won't have to worry about if that's the inclined length or the horizontal length, because they'll essentially be the same without any sense to keep track of the difference between the two. So the energy equation, strictly speaking, we'd have to factor in the cosine of the angle when we talk about the depth of the water, because if you really want to get technical about it, here's our inclined channel, and here's the water depth. It's the difference between, is it this depth that we're talking about, or is it this depth that we're talking about? This is longer. The vertical depth is longer than the depth that's tangent to the actual channel bottom. But since ordinarily the slopes are so mild that the depth y is the same as y times the cosine of the angle. So we'll just simplify the energy equation just to say y. You have another problem that asks you to define the flow regime. Frankly, I'm not exactly sure why they introduced that phrase in Chapter 10, because it's a concept that really we don't get into detail until chapters 11 and 12. But it's easy enough for me just to remind you, first of all, that we have the equation to characterize whether flow is laminar or turbulent. And when you don't have the diameter of a pipe, remember that in place of diameter, we use 4 times the hydraulic radius in order to calculate the Reynolds number. Now, this other thing is a little bit more tricky. Subcritical flow versus supercritical flow. Supercritical flow is characterized by a high water velocity, and usually you will see supercritical flow when water exits out of an underflow gate, or if it's coming down off of a very steep spillway. And we'll watch some videos of supercritical flow. In fact, did I show you video from a dam, that Oahe Dam? Yeah, they opened up those big jets of water. Okay, so that was supercritical flow. It's water that has an extremely high velocity. Subcritical flow is characterized by lower velocities, and This number is called the Froude number, this equation FR. It's similar in concept to Reynolds number, where it doesn't really have units, but it's a number where when you're less than 1, you have subcritical flow. When the Froude number is greater than 1, you have supercritical flow. And so in that homework problem where they ask you to classify the flow regime, they're saying, is it laminar or turbulent? And is the flow subcritical or supercritical? So here, V is the velocity of the flow, and Y sub H is just talking about the depth. Or Y sub H means hydraulic depth. And so if it's not a rectangular channel, if it was a trapezoidal channel, for example, then you can calculate the hydraulic depth by the area divided by the top width. So T stands for the top width of the flow. That's Froude number. Okay, so I would like you to refresh your memory how to use trapezoidal geometry, how to calculate these terms here. Do I give you a formula? I give you the formula for the section factor. The rest of them, I think that you can either look off of the... No, don't look in the notes. Actually, I'd like you to just do this from your brain. And we've done it before. This isn't the first time this semester I've asked you to do some calculations on trapezoidal geometry, but it bears repeating. So find out what is the depth of flow, and there is a way to know the depth of flow based on the side slope they've defined. The cross-sectional area, the wetted perimeter, hydraulic radius. Remember, hydraulic radius is area divided by the wetted perimeter. Hydraulic depth. Hydraulic depth is the same thing as this Y sub H. It's the area divided by the top width, and section factor. All right, so let's take a few minutes to do that. Feel free to collaborate with one another. Okay, so before we take a look at the exam key, are there any questions to the example or the announcements? You want to talk about the homework for a second? Okay, how do you digitize a curve? The way that you digitize a curve is draw a vertical line for every hour. So there's already lines there for every 4 hours. So draw a line for every hour and then take it over to the vertical axis. And so midnight is 100. It looks like if you took it at 2 a.m. it would be 95. 4 a.m. is saying maybe that's 110. And so it's already known that the peak hourly flow of the maximum day is 560 liters per second. So the highest part of this curve, they're saying, is 560. So 560 liters per second. Well, let me actually bring this up on the document projector too, because maybe I can give you a better idea if I draw right on here. I'm not sure what's going on with the document projector. Let me try rebooting it. That always helps. Well, it's not even turning on. Oh, wait. No, it sounds good. Wait for it. on. All right. Okay, they're saying right here, this 560 liters per second, that is the maximum day. So this curve goes along with the maximum day. Here's the maximum day curve. When is the peak hour of the maximum day? It's up here. So this is 560 liters per second. So if we go over here, that corresponds to 275. So 275% of the average day. So 560 liters per second is 275% of the average daily flow. So what is the flow rate at noon on the maximum day of the year? So at noon, the flow rate is going to be, if I take this over, it looks like, let's say 155 divided by 275 times 560. That would tell me my flow rate at noon. Can I get somebody to calculate that real quick? So this 155 to 275, it's like a percent of the peak flow. 315.6 liters per second. So that's what the flow rate would be at noon, because it's just a scaling factor. You can look over here on the vertical axis to find the percent of the peak. So at right here, it's going to be 100% of the peak flow, because it's 275 divided by 275. So as a part of your solution, prepare a table like a time versus a percent of peak for every hour of the day. And one of those should say 100% of the peak flow. And it should be at like around 7 o'clock. All right? It's a really simple concept, but being able to have this curve will be useful to you in sizing the reservoir. And also in demand estimation, I've already told you that the peak hour, you can consider that to be 3.25, the average daily flow, and the peak day flow is 1.8 times the average daily flow.
Typical winter day, like why is that on this?
It's just a figure that has both, and it illustrates the fact that during the winter time people use less water than the average daily flow.
So this was published.
This figure is more for reservoir sizing. For demand estimation, you just use the two factors that I've already mentioned, 1.8 to find the peak day and 3.25 to find the peak hour. All right. Let's first of all take a look at the reservoir problem on the exam. The problem that has reservoirs.